So I rushed out of the faculty meeting at 11:30, parked the car down below Flairsham over there, and left my flashers on, then taught the Kearney kids, then kind of forgot about my car. So guess what? I got a dead battery. Yeah, it's dead. But luckily there's somebody down in the physics office that's going to bail me out. Now, some of you are probably going, well, it serves you right, because you put a homework assignment for chapter 20 on there. So justice is there. But what we're going to do, since we have such a nice turnout, how many vidiots do I have here? How many vidiots? Just one? Just Sarah? The only one? Okay, the rest are regular 220 students. Okay, because we will do cover chapter 20. We'll be on the test, and we'll talk more about the test on Monday, but up through section 20-3, 20.3. Well, it's only 4 sections. We're not going to do waves yet. They threw waves in at kind of a funny spot, but it doesn't matter where you put waves in. It still works. But I thought, since what I did was I went through and I just picked problems, I thought the best way to do this, now I hope you don't think this is cheesy, but I thought the best way to actually teach this chapter is to go through your homework problems today. Okay? So we'll just call them up. And since you're all here, it's a beautiful Friday, and you all came anyway, you might as well get some out of it. And we'll work them together, and I'll bounce questions off of you. So, and since I went to Target yesterday, every semester I go to Target and spend $106.97 and get a new calculator, because I lose this every single semester. I lose my calculator. All right. So go ahead and get out some papers so that you can do this. You're not going to turn this in. There's not going to be a quiz, but here we go. And this will also help out the video people too. All right. Oh, and for those of you that were having a problem on homework on chapter 19, I figured out what it was. You kept getting the right answer and it's saying it's wrong. It was supposed to be in microteslas is the answer. Because I reworked my problems and I got them right. They worked out just fine. And remember, you're taking the distance half on those 2 wires because you all suffered enough. So now that you know how to do it, I'm going to give you a 2-wire problem on the test. So you just know that, right? You just know that that's going to happen. You're going to get a 2-wire problem on the test. You're going to have to figure out what the forces are on that wire, on those 2 wires. All right? But when you do that, it should, because I worked it out, I didn't even need a calculator. But anyway, now we're going to talk about Faraday's law. But before we get in there, of course, I've got to teach you just a little bit. Here's what we're actually looking at here. Okay? Here's actually what we're going to be looking at here on Faraday's law. All right. Now, basically, what happens is, and we'll see this in the first problem that we do. What happens is, if I've got, I'm bleeding from somewhere. I don't know where, but anyway, my nose? Really? Oh, okay. Hopefully it'll be all right. It's been one of those kinds of days. But anyway, all right. What is it? Oh, the EMF. The EMF, the voltage in a wire. Let me zoom in here a little bit. Voltage in a wire is equal to the number of turns in that coil. Number of turns in that coil times the change in the magnetic flux over the change in time. Oh, thank you. Is this starting to be a mess here? Here, let me go check this out. Hold on a second. Standing up here. God, it's like the WWE. Okay. All right. Thank you, Mr. Hill. All right. Now. Okay. What did we say the flux was? What did we say the magnetic flux was? Do you remember? NAB or NBA. Yeah, it's the NBA thing. Right. It's the number of turns or it's actually BA cosine of phi. Where, now notice this is the cosine, and that is the angle, all right? So let's say for sake of argument that the board here, that this board here is the area, and so that's the cosine off this thing. So if I tilt, well, let me do it this way. All right. So if this sheet right here is the plane of the thing, and then I've got this thing. Now this means that the magnetic field is coming out at me, right? Magnetic field's coming out at me. So it's then if I had another one that's kind of going at an angle but still coming out, okay? They're talking about this angle right here between here and here. That's that sine, that's that angle between the normal. Basically, here's the plane, here's coming straight out. If it's tilted like this, we measure the angle off this normal here. That's what they're talking about. Okay, so let's just go to the homework problems and see what they look like. They're only worth 1 point each because I forgot to put the points there. But it doesn't matter if it's 1 point or 10 points. It's still going to give you like 0.7 and they're worth the same amount. Yes?
Worth extra credit for all those ones that like we get right and submit to Mastering Physics.
Oh, you probably didn't get it right. I'm going to take a look at your thing, but it's just not what you're getting it for free. So here we go. All right. So now, what this says. I see for you already. Uh-oh, did I even do this problem? Uh-oh, I might be flailing. All right, here we go. Learning goal. Here's our EMF. Here's what we're going to be looking at here. Induced current. All right. In this problem, oh, okay. All right. So the magnetic field is coming out at you. That's what they mean by this B field. Is uniform coming out at you. A region. So this problem states this. It says, in this problem, we'll consider a rectangular loop of wire with sides X and Y placed in a region where a uniform magnetic field exists. See the diagram. So here's the uniform magnetic field coming out at us. Okay. Initially, the field is perpendicular to the plane of the loop and is directed out of the page. The loop can rotate about the vertical or horizontal axis, passing through the midpoints of the opposite sides as shown. Okay, great. All right, so basically what this wire can do is it can rotate however it wants to. All right, so now, which of the following changes would induce an electromotive force in the loop? In other words, if I start to turn this thing, then that means 1, my angle changes, and 2, so does the area. Oh, well, actually, the area of the loop's not going to change. It's going to stay the same. But the angle that's being, that's hitting it is what's going to change, I think. Okay, so which of the following changes would it, okay, the magnitude of B increases. What if we increase the magnitude of B? Will that change the flux? NAB. If we make B bigger, will that change the flux? Those snow, that's going to kill somebody someday. The way these slate roofs are like this, and then the snow melts, and those things fall like 4 stories on the passersby on the sidewalk below. So I'm going to walk out there someday. There's going to be some poor undergrad with an icicle impaled through him. All right. Anyway, whoops, that'd be a lawsuit. Anyone see The Omen, the original Omen from 1976? Anyway, all right. So, sorry. All right. So when you consider each object, assume that no other changes occur. Okay, so which of the following would induce an electromotive force? A magnitude of B increases? Yeah, that would work. If it's increasing over time, the magnitude of B decreases? Yeah, that'll work. Now, what happens when it decreases? Which way would the current? Okay, let's just play this game. Let's say the magnetic field decreases. It's going down. Which way is the electromotive force going to go? Which way is the current going to go around this wire? If B is decreasing, remember, is it going to try and help it or stop it? Help it. So therefore, you put your fingers inside and grip it like this, and so it looks like the current would go this way. If you can get your head around that, you've got 80% of this chapter knocked. Okay, if you can get your head around that, that's Lenz's law. So if this was increasing, if all of a sudden we started increasing this thing over time, then which way would the current go? Oh, wait a minute. I'm sorry. Duh. If it started to decrease, we'd want to help it so it'd go this way. See what I'm saying? I don't have this down yet. All right. So in other words, we'd want to have it come in. I keep thinking this is going in, but it's actually coming out. So it'd go this way. And so now, if all of a sudden it starts increasing, we're going to want to oppose it, so it would go this way. All right. The loop rotates about the vertical axis. Yeah, that would cause there's three ways to get the flux to change. You change the angle, you change the magnetic field, you change the area. Okay? You change the area. Those are the three ways to get it to change. So I think we're going to probably click all those off. Doop. Doop. Okay, now the loop moves to the right while remaining on the plane. It just starts moving to the right. Would that do anything? No, because the magnetic field staying the same, the angle staying the same, and the area staying the same. However, if this was like some kind of flexible conducting material, and we went like this and made it flatten and get bigger, that would induce a current also. Okay? All right. So that won't do it. Submit. I like the way they make you submit to their will. But anyway, okay. Oh my. Find the flux of the loop. Okay, fine. What do I do? Just put X, Y, B, right? That should work. X, Y, capital B. Please work. Submit to their will. Yes. We're golden. Okay, if the magnetic field suddenly decreases from B to 0 during a time interval t, what is the induced EMF? Is there any way you can like copy and paste on this? Yeah, we'll just divide by t. I'm not going to bother typing that in. So on that one, yeah, you just divide by t. Okay? All right. If the magnetic field steadily decreases from B to 0 during a time interval t, what is the magnitude of I of the induced current? Uh-oh. Ruh-roh, George. How do we find I? Oops. Oh. Now all of a sudden they throw something at us. There's a resistance in the wire. So what does Ohm's law say? Remember Ohm's law? We do yoga when we do E&M. Ohm's, right? It says what? V equals IR. Okay, so now they give us the resistance. We find the EMF, which is the EMF is the change of BA cosine theta divided by delta T. Okay, so you get BA cosine delta T. So here's what it'd look like. That equals V divided by R. So I'm going to go ahead and type this one in because it would be kind of fun just to bore you to death doing this. So we get X, Y, B. There's my flux, all right? And it's going to change with T. And then that's my EMF. And so that's V. And so then V over R equals I. Submit. Yeah. All right. Okay. If the magnetic field steadily decreases from B to 0, okay, so it's steadily decreasing from B to 0 at a time t, what is the direct, oh, there we go. There we go. What's the direction of the induced current? It's decreasing, it's going down, and we want it to come out at us, so which way is the current going to go? Clockwise or counterclockwise? All right, how many say clockwise? Okay, how many say counterclockwise? Right, because you're doing the opposite of what I told you at the beginning. Good. In other words, okay, the field's coming out at us, but it's decreasing. So we're going to want to help it. So we're going to put our fingers this way. Which way is my current going? This way. Okay? So it should be going counterclockwise, right? Wouldn't that be counter? If this is noon, this is 11. Yeah. Okay, counterclockwise. I hope this is right. If it's not, class dismissed. Woo! Good. All right. Now that I said that WWE thing, I'm like Ric Flair up here. All right, now, you all are too young to remember Ric Flair. But anyway, no, you're not. You're not. You still remember Ric Flair? All right. And the Ultimate Warrior. And who is the one guy? The Ultimate Warrior. And who's the guy with the glasses and the cowboy hat? And he had Miss E or whatever. Oh, yeah, Randy Savage. Yeah, Macho Man Randy Savage. Sorry. Yeah, some people that didn't grow up here in the United States are going, they have lost their mind. I want to go home. All right. Which of the following changes would result in a clockwise? Oh, which of the following? Okay, now we want this thing to go clockwise. So what are we going to do? It's going to go clockwise. So now what are we going to do? What can change to make it go clockwise? Yeah, if we increase the thing, then we're going to want to oppose it coming out. So the magnetic field increases, yeah, that'll work, because we're going to want to go the other way. Let's say the loop rotates through 45 degrees about the vertical. Oh, see, this stuff is all that 3D stuff. I can't picture this. I don't know. Let's just take, what's that? Show answer. That's cheesy. I like the first one. Okay, we'll show the answer. I don't care. I've lost all my pride. Oh, that's the only one that worked. Hey, I knew that. Okay, let's continue. Let's pretend that never happened. Now, this is a horrible problem. No, this one's okay. All right, now. Okay, now this is a coil. Basically what we have here is an ammeter. It's measuring the current. Okay, so, all right, so now I'm dropping this thing through here. Let me do this. I'm sorry. Let me do this. That did nothing. There you go. Now you can kind of see it, but you can't see the answers really. Okay, that works. All right, now we're dropping this down. So this thing's increasing. This thing's increasing and it's going down. So if it's going down, which way is the current? Do we want the current to go to oppose this thing? Yeah, we want the magnetic field to go up. So it'd be a current that's going around this way, which would be what? Counterclockwise? If the speed of the magnet is doubled, the induced voltage is, oh, that's not even what they're asking, is it? If the speed is doubled, then that would mean the voltage would probably be doubled. I hope it's a linear thing. If it's not, I don't understand this stuff at all. Twice as great? I hope so. Because there's no, oh, good. Oh, sorry. Sorry, Hal. Didn't mean to do that. All right. Okay, the same magnet is plunged into the coil. They're getting exciting here. All right. The same magnet is plunged into a coil that has twice the number of turns as before, as shown in the figure. If the speed of the magnet is again V, the induced current is, oh, remember, it's N, so if it's got twice as many turns, what does that do? That increases our, no, it does. Because remember, it's N delta B over delta T. So the B will be changing with time because it's falling through there at a constant speed. So therefore, if I double the turns, I double the EMF, so therefore I should double the current. I don't remember picking this problem. I don't like it. Oh, try again, loser. Okay. What? It's unchanged? Did you already try that?
Well, I didn't put in twice as great. I put in unchanged, and it was right.
Oh, but we don't know why. It says here, recall that, oh, to show us why? Yeah, I did these. Okay. By increasing the number of turns, the induced EMF increase. That's what I thought. But so does the, those dirty birds. That's like one of those multiple choice questions that everyone's going to miss. Okay? Which we're not going to have on the test. I'm going to give you short answer things. So if I increase the number of, so I was right up to here. Then I forgot about this part. Okay, so the resistance increases. All right, so that was kind of fun if you like all-night dentistry. Okay, now, all right, now here we go. This is good calculations. I'm much more happy here with good old calculations. Exercise 20.2. Okay, circular. This is the type of thing. Actually, that first question would be more like a test type thing, and this is definitely up there for test. What is the flux of the loop's plane if it is parallel to the field? Okay. All right. So a circular loop. Oh. So think of this. All right. Think of this. We got a circular loop. Okay. Now then, if I got a magnetic field coming through the loop here, that's a good thing, right? If we're increasing the magnetic field or something like that, then I get a nice coil. But what happens if it's parallel to the field? There's parallel. Now what's going to be the flux? 0, because there's nothing passing through it. Okay, it can't pass through. All right, so I'm going to say 0 just to be bold and daring here. Let's see if that's true. That's a 0. Yes. My 0 is correct. Yeah, for some reason it only gave me half a 0. Okay, what is the flux of the loose plane if it is an angle of 39 degrees to the field? How would we do that? B. Exactly. BA times the cosine of theta. So you just type in 1 times 10 to the negative 2 meters. That's A. Oh, so we don't even have to, oh my goodness. The cosine of 39. Yeah. So whatever that's going to be. Well, I can do it real quick. Oh, I don't need to waste your time with that. Just make sure on 20.2 part B, it's BA times the cosine of theta. And you've got it. Okay? It says, what is the flux of the loop's plane if it is perpendicular to the field? Now what happens to the cosine of theta? What's the cosine? Yeah, it's cosine 0, so the cosine of 0 is 1, so therefore it's just B times A. I can do that one. 0.2 times 0.01 is 0.002. I'm going to try that, see if I can still do decimals in my head. This will be embarrassing. It'll be wrong. I know it is. And then I'll get all mad. No, there it is. We got it. Now, if I take that, multiply it by the cosine of 39, 2 second e to the negative 3 times the cosine of 39, I've got the other answer, which is 0.0015. So let's try it. 0.00155. And it'll probably tell me something, give me some nasty comment about sig figs or something. Try again. Okay, we'll move on. All right. That's the way I try again. That's the way I roll. All right, now. Maybe we're supposed to use 61 or 51 degrees. If it doesn't work, try use 51. But it should be the cos. You see what I'm saying? But it should be off the perpendicular like that. So it should be 39. So it should have been. I might have typed in something wrong. All right. So a square loop wire. So here we go again. Here's the same thing again. If the field strength is initially 110 milliteslas, not micro, milliteslas, and it decays to 0 in 0.05 seconds, what is the magnitude of the average EMF in the loop? Here we go. It's just the magnitude of, what are they asking? The average EMF. So the EMF, it's got a square loop with one turn, and it's got sides of 48 centimeters, so that would be the A. How would we find A? 0.48 times 0.48 times 110 times 10 to the negative 3 Teslas divided by 0.015. Okay, and they just want the magnitude. They're not asking for the polarity. So I'm going to go ahead and put that in just because I'm rattled now. Yeah, here you go. Here you go. Here's the .cam thing. All right, so basically they said this. That, well, let's just take a look at this. This is 48 centimeters. This is 48 centimeters. And we've got a magnetic field that's coming straight out at us here, like this. We've got a magnetic field coming straight out. Let me draw it here. Say it's perpendicular. This is uniform magnetic field. And B was equal to 110 times 10 to the negative 3 Teslas. And so A is equal to 0.48 times 0.48. Oh, wait. 0.48 times 0.48 equals 0.234. 0.2304. And I go ahead, and what I figured out that helps me to get, so I don't get the try again, and then I get all angry, and the physics department learns new words, is I go ahead and just keep all these numbers all the way through my calculation, and then go to 2 sig figs when I'm finally done. All right. So, and then what they say the delta T was what? 0.015? Okay, good. So here's basically, and it's perpendicular, so the cosine off the angle off the normal is 0. All right. So the EMF then, the magnitude of the EMF would be BA cosine of 0, which will equal answer times 110 second e to the negative 3 equals 0.0253. So I'm just going to put in 0.025. Oh yeah, here's my new calculator. Isn't it nice? All right, now come over here. What did I say the answer was? 0.0253.
I thought you said you were taking 0.48 times 0.48 times
The B field.
110 times
And then you divide it by t. Oh, I forgot to divide by t. Very good. Now divide by 0.015.
Where did you get the cos theta in there? There's something about it in the table.
Yeah, it says it's perpendicular to the area. So if it's perpendicular, that means it's at 0 degrees off the normal.
So you did cos 0?
Yep, which is 1. Cosine of 0 is 1. Okay, so somebody saved me from myself. So it comes out to be 1.7 volts. 1.7. Enter. Oh, you don't enter here. You submit. That's right. You don't enter things. You submit to their will. Oh, it's wrong. Loser. What happened here? Okay, so we take 110. Second, I don't want to waste your time anymore with this. Second, negative 3, right? Oh, it's 46. Oh. Times 0.46 times 0.46 equals divided by 0.015. 1.55. Aha. So I'm going to go 1.6. There we go. Whew. I did better yesterday. All right. What would be the average? Thank you for pointing out that all I did was transcribe it wrong. All right. And sometimes I know when I get emails from people saying, I've done this 100 times. Oh, you're using 48. You should be using 46. Oh, sorry. I do that too all the time. What would be the average EMF if the sides of the loop were only 23 centimeters? Ooh, we can't just cut this in half. Yes, sir.
Why do you not change the Teslas to use milliteslas? Yeah. Oh, okay.
Yeah, 110 to the negative third. Yeah. Yeah. The Teslas didn't change. The magnetic field there, it's because, see, we consider.
Yeah, I was just wondering about the units because I didn't think it would come out right.
Yeah. Okay. So if we have this thing, if we have the sides, just don't take 0.8. That won't work. That won't work because we're squaring that thing. So it's going to be 0.23, 0.23 times 0.23 times 110 second. Oh my gosh, I'm wasting your time. We got to move on. Okay. Y'all can get it from there. All right, now, because we've only finished 5 problems. Okay, now, this is all the same thing. This is all when the magnetic flux through a single loop increases by 33. Wow. Whoa. That's huge. An average current of 34 amps is induced in the wire. Okay? Huh. What the heck are they asking about here? Assume that the wire, oh, there we go. Assume that the wire has a resistance of 2.2 ohms. There we go, because we needed that. You still, don't forget, V equals IR. He's still out there. He's still your buddy, okay? And so, and that V is actually what you're getting when you do the NBA times divided by delta T, okay? NBA divided by delta T and the cosine of the angle. All right, so that's your voltage. And so if you take that voltage and divide it by, so they want us to figure out what delta T is. That's tricky. Let's do it. Let's do it. This will be fun. Now I'm going to transcribe this one properly, and then we'll fly through some more of them, because I haven't even taught you about transformers yet, but I wanted to make sure that we got this part down cold first. Oh, this is a difficulty of 1. I should be able to do this. Okay, so we've got B equals, we're going to increase, change in B, actually. Change in B, oh, yeah. Oh, but then I have no idea. Hold on a second. Let me get what the units are, because I don't know what it is till I write it down. Then I'll change it back when 33 Tesla. Oh, this is the change in BA. 33 Teslas per meter squared. Notice it's 33 Teslas meter squared. That's BA, right? Ha! They're trying to be slick. Okay. An average current. So when I've got 33 over delta T, I'll show you this all in a minute, 33 over delta T divided by, that equals I times R. Okay, so now I've got it down. And R is equal to 2.2 ohms. All right, so here we go. All right, so now we can go to the dot cam. Here's my madness so far. All right, so in other words, here's my BA divided by delta T equals I times R. And they told me, I forgot what I was. What was it, 34? 34 amps. That would bite you pretty good. If anybody's dealt with electricity before, which I refuse to do, that's why I don't bring in too many demos. That's why my friend Mike Kelly's bringing in the demos on Friday, because he doesn't mind getting bit by this stuff. All right, so basically, how am I going to find delta T? Looks like it's going to be 33 divided by IR to me. Should work. Looks like it's fraught with peril, though, with punching it into the calculator, but that should work. Okay, so basically, you're going to get 33 over IR equals delta T. That should do us. So we get 33. Oh, we need to move on. Okay. And then the second one would be the same thing. If the current is only 17, how long would the flux increase have taken? Okay. If the thing was only 17. Now, let's talk about back EMF. I think that's the next thing we're going to be talking about here. At least I hope it is. Oh my. Gosh, how many of these things did I give you? I think I've beaten this horse to death, right? We know now that NBA divided by delta T, NBA cosine of theta divided by delta T equals the EMF, right? You hold a wire coil perpendicular to a magnetic field. Good. Let's just go through this real quick. If the magnetic field B increases while its direction remains unchanged, how will the magnetic flux of the coil through the coil change? Okay, so in other words, the magnetic field is increasing, but its direction is unchanged. How will the magnetic flux through the coil change? The flux is unchanged. Is that true? No, because the magnetic. So basically, you've got pretend this is our coil. You got a magnetic flux coming through here. If I increase that will change my flux, right? Because it's NBA. If B gets bigger, then my flux gets bigger. Okay? The flux increases. Yes. No. All those are wrong. Yes, we're right. I knew it. We're golden. Okay, if the B is kept constant, but the coil is rotated so that it's parallel. Ooh, so now we got this thing, B field coming out at you, but now I'm going to take this square and rotate it sideways. Is there any B field able to get through it now? No, so what's the flux? Zero. There you go. Do we have that as an option? The flux decreases because the angle changes. Yeah, the flux is unchanged because the area of the coil is unchanged. Nah, the flux decreases. It goes to zero. Yeah. In fact, the minimum value is zero, like we said right there. Okay, good. So that was actually kind of, I hope, worth your while to go through those first 6 problems. Now, here's my favorite problem. This really explains the whole thing of what's going on. This is a nice one. What time is it? Okay, we probably won't get through, we probably won't do a problem in a minute here, but we'll at least get started. Transformers are real easy. You could read that on your own and figure out the transformer problems. They're not too bad. Okay, but I'll explain it to you on Monday. So we finish the chapter. So this works out pretty good. Okay, in the figure, a conducting rod of length L of 27 centimeters moves in a magnetic field. Okay, so it's moving perpendicular to this magnetic field. of 0.44 teslas directed into the plane of the figure. The rod moves with a speed of 7 meters per second in the direction shown. Okay, now don't forget FIB, or right, IBL equals the voltage. But anyway, here's what happens. When the charges in the rod are in equilibrium, which point A or B has an excess of positive charge? So here's what's going on. Now think about this. We got this rod coming down here, okay? And it's a conducting rod, all right? It's a conducting rod. So if it's moving this way through a field that's this way, all right, through a field that's this way, which way? No, field's going the other way. Oh my gosh, how do I do that? Like this. There we go. Here we go. Field's going in, rod's going down. Which way is the force going? That way. It's going from A to B. So what it's doing is it's pushing all this charge this way, here to point B. Okay, it's pushing all these. And what we say is, actually what's going on is the electrons are coming back here, but we say that the protons are getting pushed up this way. Either way. So when the charge is in equilibrium, which point A or B has an excess of positive charge? Which is it? B, because that's the direction the force went. That's the direction the force went. Please be right. Thank you. There you go. Okay, F equals QV times B or whatever, or F equals I. And remember, QV over T is the same thing as IL. Okay, what is the direction of the Ooh, it created an electric field, right? Because now basically what we've done is we've turned this into a battery. We've turned it into a capacitor. So here we've got positive charge here, negative charge here. Which way does the electric field go? B to A, right, because I got all the positive charge over here, and so the electric field goes away from the positive charge. B to A, very good. All right. Now, when the charges in the rod are unequal, what is the magnitude of the electric field? Oh my. What did we say the electric field was? Do you remember that equation? F equals QE, right? F equals QE. What else does F equal up here? F equals MA. What else? Oh, did you hear that? Did you hear Mr. Bishop? F equals QVB. So, QE equals QVB. What crosses out there? Q. So what does the electric field equal? VB, exactly. Keep that in mind, because when we get to electromagnetic waves, the electric that move at the speed of light, the electric field caused by that electromagnetic wave equals the speed of light times the magnetic field that's being created too. Okay, so that was kind of cool. So it's VB. What was V? 7 times 0.4. Oh, dang. I got to do a calculator. 7 times 0.44. 3.08. Ta-da. All right. Now this is asking, the reason I like this problem is because it harkens back bad memories of chapter 16 and stuff. Okay? At which point A or B has the higher potential? Where is all the positive charge? So, where's the higher potential? What is the formula for potential? V equals KQ over R, right? So in other words, a bunch of positive charge has higher potential, right? A bunch of negative charge has lower potential. Somewhere in the middle is the zero potential, right? Yes, I believe it is B. Uh-oh, after all that, I hope I'm right. Yes. It says, what is the magnitude? Oh my goodness. What is the magnitude of VBA? Do y'all remember Do y'all remember there's a funny way to get the voltage if you know the magnetic field? What is it? Multiply what? Something. Yeah, we're going to multiply something. Going to multiply something. Remember the capacitor stuff where we had the E field times the distance equaled the voltage on the capacitor? Remember that? So E times D. What did you, E was 3.08 and this distance. So it's ED. Voltage equals ED. Oh yeah. Now I remember. All right. This was a good problem to go through. Okay, what is the magnitude of the motional EMF induced in the rod? That's the same thing as your ED here. So this ED will be this ED, okay? And if you don't believe me, let me type it in. 3.08, how long was it? 0.27? 0.83 should be. And that's what the motional EMF is in there. Whoops, wrong one. There we go. There we go.
What equation did you use for the...
Oh, here you go. Dot cam. Here you go. Voltage. Voltage equals E times D. And you figured out E is equal to V times B. So the voltage, where this is velocity. Okay? So actually the voltage equals VB times D. Which is that's kind of cool. Which makes sense. Look. This is meters per second, right? Meters per second. Meters times meters is what? Area, right? It's an area divided by seconds. So you got BA divided by seconds. Doesn't that equal the voltage? Ta-da! See how it all ties together? I love it when a plan comes together. Okay, now, one more. Let's do one more. This is so much fun. I can't remember. It's the same answer. Hey, don't get greedy. All right, now. All right. Oh, I haven't taught you anything about this yet. We got this. Oh, boy. 48 minutes into class, we ran into a sine curve. I think that's where we'll stop. All right. It's a good place. We only got 5 problems left to do. Come Monday, and you'll see the end of this movie. All right. Which will only take us about 20 minutes. We did the hard part already.